This is Dr. Carroll, and today's video is about tree terminology. It's going to lay the foundation, the roots for our other videos about trees. And there's several terms that we need to establish that you're probably familiar with, but we just need to make sure that we're very concrete on. First of all, what is the definition of a tree? So if you have a tree T, it's the set of nodes and their connections. By connections, we mean a root to its children, and that sort of connection. And so, furthermore, there needs to be a specifically designated root node, and then all other nodes are what we call subtrees from the root. And then you could apply a recursive definition. Let's look at some examples. Here's a tree with this node with O in it being the root. Here's a tree, 5 here is the root, and so you could say that 4 is a subtree of 5 and 8 is a subtree of 5. Here's a tree with A being the root, another tree, another tree. So here we have several examples of trees. Our next definition is a binary tree. Now a binary tree is a subset of trees, and that there's a couple ways you can have a binary tree. One is that it's empty, or two, that we have a root and two binary trees that are its children. So each node can have at most 2 children. They may be empty or may not be. And then we refer to them as a left and right subtree. And then the definition is recursively applied to the subtrees. So let's look at some examples. This is not a binary tree because this node here and this node here have 3 children, and therefore it's not binary, meaning 2. This tree is not a binary tree because we have 3 children from the node that has 4 in it. This one is. Some of the children aren't present. For example, the right subtree of C is not there and the left subtree of D. This one is a binary tree, binary tree, binary tree. And here's a binary tree. This one happens to be my pedigree. This is me. This is my parents. And so it works very well for genealogical data to represent it in a tree form. And that there's an individual and comes from two other individuals, and so a mother and a father, and it's binary, and so you can trace it back until a long time. Okay. A root. We've talked about a root, and specifically, it's a node that has no parent. Okay, no parent. A parent then is of a node, and we'll say of another node if there is an edge from N to M. Okay, so let's look at an example. Here, B is the parent of C if there's a directed edge from B to C. C is the parent of D. More generically, 4 is the parent of 2 here, and it's also the parent of 3 and 1 as well. Okay. So a child is then the reverse. If there's a directed edge from the parent down to the child, then that defines that relationship. Then ancestor, you can think of back to the example shown here. Sorry, no, that doesn't work. So an ancestor is a node along the path from where you are. Let's take D, for example, here, back to the root of the tree. So B is an ancestor and A is an ancestor because they're on the root back. Okay? On the path from where you are back to the root. Similarly, a descendant then is on the path from the root, or from that node, wherever it is, to a leaf. Okay, and so E is a descendant of B, D is a descendant of B, and G is a descendant of B because it's along the path to a leaf. Now C and F and A are not descendants of B. Okay, you can imagine it's directed, and so then it has to be on a path to E. You can't go backwards. You can't go the wrong way of an arrow, so to speak. So a leaf, then similar to a root, is that a leaf has no children. Okay. Sibling are nodes which have the same parent. A binary tree, if you're the left subchild, then your sibling's the right subchild. In a general tree, you could have multiple siblings, okay? Or you could have no sibling, and you could also have no sibling in a binary tree. It just depends if there are other children of the same parent. Okay. Now let's talk about the level of a node. So first off, root is at a level 1. Now that might be a different definition than what is given in other courses, but for this course, the definition of a level is that root has a level of 1. Okay. And then for a node that's not root, then it's the number of nodes from the root to that node, including the node itself. So for example, 3 here has a level of 3. 1, 2, 3. F here has a level of 1, 2, 3, 4. Okay? And then when we want to talk about the tree as a whole, we talk about its height. And the height is the longest path from the root to a leaf. So it's the maximum level of all nodes, okay? And then empty trees have a height of 0. So this tree has a height of 1, 2, 3, 4, 5 because this is the longest path. This tree has a height of 1, 2, 3, 4, 5, 6, 7. This one, I don't know. Actually, I do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, if I counted correctly, is the height of that tree. So now let's talk about a full binary tree. So we're talking about a binary tree, and it's full, and we need to specify the height. So full means it has all the nodes it can possibly have for a binary tree, okay? All the nodes that can possibly have. This is not a full tree. I mean, in reality, it is. I just have some more research to do to fill out the tree, okay? But this is a full binary tree. Every node that has a child has 2 children, okay? This is not a full binary tree because it's missing the node, which we would probably number 26 here, 27, 28, 29, 30. It's missing all of those nodes, and so this is not a full binary tree. But what it is it's a complete binary tree. So a complete binary tree, again, we need to specify the height, is it's full down to the level the level just before its total level. So it's full at this level here and up. And then all the nodes are filled in. You could think left to right. So it is complete, even though it's missing, it's not full here. It'd still be complete if we removed this node, this node, this node, still complete. If you remove the nodes left to the right, but if we remove node 14 or 13 here, it would not be complete. Okay? And then balanced is that for any node in the tree, that the height of the left subtree and the right subtree is within 1 of each other. So it's not lopsided, it would be the opposite of that. So complete trees are always balanced. Full trees are always balanced too, because all of the height for any node, the height is going to differ by 0 for a full tree. For a complete tree, the height's going to differ at most by 1. This tree is not balanced. This line here, my 24th great grandparents here, is the extreme example showing that my father's line has more research done than my mother's line. I attribute that because my father's has a bachelor's degree in genealogy. Is this tree balanced? No, by no means. Notice it doesn't even have a left child here. That doesn't make it balanced, except that there's this, we could say, grandchild of B, not making it balanced. Not balanced. Is this one balanced? Well, the question is at every node, is it balanced? Balanced, balanced, balanced for this node. This node, this tree has a height of 1, 2. This one has a height of 1, 2. Great. This node, we have a height of 1, 2, 3. This one we have a 1, 2, 3, 4. Okay, so from this perspective, it's balanced. But from T here, we have a height of 1 on the right and then 1, 2, 3. So this tree is not balanced. Okay, is this one balanced? Yes. Okay, and balanced again. Okay, a binary search tree then is a binary tree, but we pay specific attention to the ordering of the values on the tree, and that is that all the values in the left subtree are less than the value of that node, and that all of the values in the right subtree are greater than or equal to the value of that node. And then, of course, it's, again, a recursive definition. And we'll spend a lot more time and go a lot more in depth in binary search trees